Thank you for being here, and thank you to the organizers, Valentin and collaborators, for inviting me. It's a great pleasure to be here in this beautiful setting. So today, I was asked to give the first talk of the day in this session on laboratory astrophysics. And so I thought I would give a kind of an overview of some recent progress in calculations of molecular collisions, so studies of molecular collisions from the theoretical side. I'll start with a very short introduction. I think most of you are aware of the importance of collisions in astrophysics and astrochemistry, but for those of you who are not, the point of studying molecular collisions is that in many cases, in many environments, you are not at local thermodynamic equilibrium. So you cannot assume that the populations of the rotational levels or vibrational levels are determined by a Boltzmann distribution. And this is because of the competition between radiative and collisional processes. This is shown here on this very simple diagram with two levels, where we have excitation and de-excitation by photons, given by the Einstein coefficients A and B, and collisional rate coefficients C. And because the densities are usually quite low, you cannot assume that everything is equilibrated, and you have to account for this competition between radiative and collisional processes. This is important in particular to interpret observations to get accurate molecular abundances or column densities, if you prefer. This also helps to put more constraints on the chemistry that's going on the chemical models, because it informs getting an accurate abundance is important to understand formation and destruction pathways of molecules in the ISM in particular. And they can also be used to probe the temperature of these environments. In this context, some molecules such as ammonia, the HCN over HNC ratio, or methyl cyanide are used a lot. The example of ammonia is shown here. You have this rotational diagram with the energy on the y-axis and the value of the quantum number K on the x-axis. Blue is ortho levels and red are para levels. And the transition between the lowest state for each value of K is forbidden by radiative processes. It can only occur through collisions. And so, for example, this transition between the 2,2 to the 1,1 level can only occur through collisions. And so if you know collisional rate coefficients, the probability for this transition due to collisions, you get information about the temperature. And you can also get information about the density of the local medium. So to do these non-LTE radiative transfer models, typically you need rate coefficients for these collisional processes for collisions of molecules with helium, H2, and sometimes hydrogen atoms as well, over a range of temperature of interest. I put here 5 to 500 K. That's just an indicative number. It depends on the environment, obviously. The general methodology for these types of collisions has been developed since the 1960s. So this is not a brand new field, but it has gone through many evolutions since then. And there are new developments that are still occurring today. And the general idea and the general methodology is relatively simple. First, you need to study the interaction potential between the two molecules that are colliding, denoted here by A and B. So you have a potential that tells you how these molecules interact. Then you study the dynamics using this potential. So you fix a collision energy, and then you look at the dynamics governed by this potential. And from there, you can calculate cross-sections, shown here as a function of the energy, which essentially gives you the probability that the excitation occurs when the molecules collide. And once you have that, you can calculate the rate coefficients by integrating here over a Maxwell-Boltzmann distribution that gives you the rate coefficient as a function of temperature. That's the overall methodology that we use. Now, for the first part, the potential energy surface, you can, you have to calculate it ab initio, so with quantum chemistry methods. And the first complication is the number of dimensions of this potential, the number of coordinates that it depends on. This is between 2 and 6. If you look at rotational excitation, you have some examples here. The atomic molecule plus helium, for example, you need 2 coordinates. 2 linear molecules, you need 4 coordinates. Non-linear molecule plus H2. This is the example of methyl cyanide. You need 5 coordinates, etc. so you need to do these calculations for a grid of geometries, distances, angles, etc. And one of the main issues is that these are weakly bound systems because it's the interaction of a molecule with helium or H2. This is governed by dispersion interactions, so you need very accurate quantum mechanical methods. Typically, the size of the well is between 20 and a few hundred wave numbers. This is rather small. And the gold standard is this couple cluster method with large basis sets. And again, typically you need points in the range of 1,000 to 100,000. So this is already quite a daunting task. Then you need to have a representation of this potential, a global fit. This is an example here for the case of methyl cyanide shown here, where you have the isoenergetic contours of the energy as a function of the distance between the two molecules and the angle theta that is defined here. In red, you have the attractive part. In blue, you have the repulsive part. And you see this is very anisotropic. It depends strongly on the angles. So again, you need to calculate a lot of points. So that's the first step. Then the second step is the dynamics. And there I listed here a bunch of different methods that are commonly used. I will not go into the details of those. I will focus mostly on the left-hand side here with the inelastic collisions. The most accurate method is the one in red, close coupling. This is a fully quantum mechanical method. So that's the reference against which you benchmark other methods, all these other methods, which are all either approximate quantum mechanical methods or classical methods. And the common feature of all these methods is that you need a potential. You always do, right? And so I will just spend a few seconds explaining the point of this close coupling method. I think you will hear more about it later, maybe. But just so you understand the problems that we have, since it's a quantum mechanical method, we are trying to solve the Schrödinger equation. The Hamiltonian is shown here. You have two molecules A and B colliding. You have a Hamiltonian for A and Hamiltonian for B, and then this is the relative motion of the two molecules. Then you write your wave function as an expansion here in terms of angular functions. I will not bother you with the form of these functions, and radial functions for the distance. Yeah. You put this in the Schrödinger equation, you integrate over all the angles, and you are left with a set of coupled equations shown here. The coupling is in this sum, yeah, the sum over alpha. These are the angular functions shown here. And this is where all the problems come from, because these are coupled differential equations, and there can be thousands or tens of thousands of such equations, and obviously this is hard to solve. Yeah? And the number of these equations depend on how many terms you put in this expansion. That's really the main issue we have. If you solve these equations, you get your cross-section, then you get your rate coefficients. And if you have that, you can then use them to look at non-LTE modeling. These are three examples. The first one at the top is a very nice one by our next speaker on methanamine, where you have the LTE model in green, the green line here. It doesn't work at all. And then the non-LTE model in red, which reproduces observation almost perfectly. Then you have another example here. This is for deuterated ammonia. And this is another one for methyl cyanide, which shows the excitation temperature as a function of the density of H2 here. And you have the typical situation where you have at low densities photon equilibrium, at high densities here collisional equilibrium, and in the middle non-LTE regime where the excitation temperature can vary quite dramatically. Yeah. All right. On top of that, we also have experiments. I'm not an experimentalist, obviously, but it's important to mention that there is a collaboration between theorists and experiments have been performed for a few systems which have validated theory, essentially. This is the example of CO, H2, and here O2 with H2, and you have the comparison between theory and experiment, and it's almost perfect, right? These are experiments performed here in Bordeaux by Astrid and collaborators, and there is another group in the Netherlands which uses a different setup, but they can also study these inelastic collisions. This here at the bottom is the example of NO with H2, and they are so accurate that they can discriminate between different potential energy surfaces of different quality. Yeah. So overall, I would say that for these specific small systems, theory has been validated, which is good. It means you can use it for a lot of other systems which are not doable experimentally. Yeah. So to come to the recent successes, I think the methodology to study these collisions is quite clear, quite well established. It is validated by experiments. You can use it in other, I'm focusing here on rotational excitation, but you can also look at fine structure, hyperfine structure, these type of things. There is development of new approximate methods. I will come back to that soon. We have data in the form of rate coefficients available for about 70 molecules, which is both good and bad. It's good because 70 is quite a lot, but at the same time, you all know this figure. It's not up to date, by the way, but there is a lot of detection of new molecules, especially in the last 5 years or so. It's not clear that we need rate coefficients for all of them, of course, but still, today we have almost 300 molecules detected. So this number of 70 is quite small in comparison. There are a lot of a few databases available, EMAA, Basecall, and Lambda in particular, which contain all these rate coefficients that astronomers can use. And in particular, these types of studies have, I think, led to improved interactions between the astrophysical and the chemical physics community. I don't think I have to tell you this. You're very lucky with the PCMI community, but this is, I think, it's one of the successes. All right. Now, in terms of recent challenges, I identified 4. The first one is related to all these new detections. It's the fact that the molecules detected increase in size. You have these carbon chains, you have cyclic molecules, and I learned last week that cyanopyrene was detected 4 cycles. And those are a big challenge for theory, for these calculations. A second one is vibrational excitation. You have the example there of CO2 and ammonia. This is, again, a big challenge for theory. A third one is collisions involving 2 heavy molecules. This is the example of water with CO. This is important in comets, for example, or in some moons of Jupiter. And again, I will explain why this is problematic. And the last one is what happens when you have ions in particular, which can collide with molecules or with H atoms or H2 molecules and both react or undergo inelastic collisions. When you have the competition between those 2 processes, this is also quite hard to calculate. So the first one is the increase in size. Most of the challenges are numerical. One of the challenges is the potential energy surface. You have the case here of HC5N, the cyanopolyne with H2, and this shows the potential energy surface. The yellow part is repulsive here on the sides, and the blue part here is attractive, and so you have something that depends extremely strongly on the orientation of the molecule, which implies some numerical problems. And the other problem is the density of rotational states. So you have these heavy molecules. They have a very dense rotational level structure. You have a very simple example here, CO. You have 6 levels up to about 60 wave numbers. And this is benzonitrile. You have about 100 levels below 10 wave numbers, right? And we have to include all these levels in our calculations. So you can immediately understand that the number of equations to solve blows up completely, and this is quite hard to deal with. Now, there has still been a lot of progress recently. I put some of the molecules here. This is not an exhaustive list. So for some linear molecules, some non-linear molecules, methyl cyanide, methyl acetylene, vinyl cyanide, propylene oxide, methanol, and some cyclic molecules. You will hear more about that in about 30 minutes or so in the third talk of the day. And you will see immediately that most of these calculations are done for collisions with helium because it's simpler, and a few of them with H2. But this is one of the problems that we have to solve to look at these collisions with H2. There is another problem related to the size of these molecules, which is that the bigger the molecule, the lower the vibrational mode. You have some numbers here. If you look at HC7N, the first vibrational mode has an energy of 64 wave numbers, or about 90 Kelvin. This is really low, right? And so normally to do these calculations accurately, you would need to look also at vibrational excitation. And that brings me to the second challenge, vibrational excitation. One reason I just mentioned, and the other reason, of course, is just the JWST. You have here an example of a spectrum taken from a protoplanetary disk from this paper here, where you can see features of CO2 here, water is here, acetylene, HCN. And so you need to understand the excitation of these molecules, the vibrational excitation. The number of calculations that have been done for these sorts of processes is quite small. You have a list here. Unfortunately, this is almost an extensive list, so it's not a lot, and it's mostly, again, for helium. There are a few cases for H2, for diatomic molecules, and then for water in particular, but the rest is for collisions with helium. And the reason, again, is numerical. One reason is that if you want to treat vibration, the potential energy surface has to include the vibrational mode. So it increases the dimension of the potential. That's one problem. And the second problem is always the same. You have more, if I go back to my close coupling equations here, you have more terms in this sum. Yeah. If you include one vibrational level or two vibrational levels, you just double the amount of equations, yeah, because you have all the rotational levels in both vibrational states. So this increases quite quickly as well. On top of that, you have problems because typically collisions with H2 behave very differently than collisions with helium. So you really need to look at H2. And on top of that, if you're looking at vibration, it's usually at high temperature, and then you need also ortho H2, not only para H2, which is, again, not very easy to do. So the conclusion here is that we need new approximate methods. I listed a few of them here, which need to be benchmarked. That's really important to understand the validity of these approximations. Good. Now, I know I still had one slide about this on one particular case, which is ammonia, something I've worked on recently. So this is the excitation of the umbrella mode of ammonia, so the vibrational excitation of this mode. And some results are summarized in this figure. It shows the distribution of the log of the rate coefficient for vibrational transitions. Yeah? And this is given in terms of a kernel density, because in this plot, there are about 1,000 transitions. So this is a little bit hard to interpret. And you can see the evolution with temperature. This is 20K, 100K, 300K. Typical rate coefficients for rotational excitation are of the order of 10 to the minus 11. And here you see this is 10 to the minus 17. So it's much, much smaller, but it changes very quickly with the temperature. At 300K, we are already at 10 to the minus 15, 100 times larger. So this is very different from the case of rotational excitation. And on top of that, for collisions with H2, you expect larger rate coefficients as well. So this is quite important to look at. Now, a third complication is, as I said, collisions between two heavy molecules. What I call heavy is very simple. It's heavier than H2, to be clear. But this leads to a lot of issues. And this is important in particular in comets. Because in comets, the coma, the atmosphere of the comet, is composed mostly of water, CO, and CO2. So then you need to understand collisions involving those molecules. So you have molecule plus water, CO, CO2. This is really difficult to do. And in the quantum mechanical calculations kind of break down because it's impossible to solve them. Just the size of the equations is, the number of equations is too large. Then one way to do this is to involve a statistical approximation, which is represented here very schematically, where you have the colliding molecules, which reach the well of the potential, and then you have a redistribution, kind of a scrambling, and you assume that everything is redistributed equally, so statistically. And it turns out that this works quite well at low temperature, because at low temperature, you have a lot of time. The collision is slow, so you have a lot of time to do this redistribution. And this is really nice because it's completely complementary to other methods, other approximate methods, which typically work better at high temperature and break down at low temperature. We use this for some cases. This is the example of water-CO collisions. And this graph shows the population of the CO rotational levels. You can see the labels here, J equals 1, 0, 2, etc. as a function of the density of water here. And you have, well, different temperatures, 10K, 50K, 100K, and you have three regimes dominated by photons at low densities, LTE equilibrium at high densities, and then this non-LTE regime in the middle. And if you look at where the non-LTE regime is, and you translate this into the distance of the molecules to the center of to the surface of the comet, which is shown here. These are the same dashed lines as these ones. And you look at what this means in terms of distance, you see that the non-LTE regime is, roughly speaking, between 300 and 70,000 kilometers from the coma. So this is quite a big region. And this has been done for a few molecules listed here, but more work is in progress. Okay. Then the last challenge that I wanted to talk about is what happens with ions. Of course, it's not all ions. Some ions are not reactive when they collide with H atoms or H2, but some of them are. This is the example of CH plus H. You have three possible outcomes. First one, inelastic. Second one, exchange of a hydrogen atom. And the third one, the insertion reaction. And in some cases, you need state-to-state data. So for initial vibrational rotational levels to final vibrational rotational levels. And this is quite difficult to calculate, in particular because the depth of the potential, which is represented here, is very large. In the case of CH plus H, it's almost 5 eV, to be compared to the numbers that I gave earlier, which are a few hundreds of wave numbers. This is a lot larger. And this makes the calculations really demanding as well. Now, again, we can use the same type of approximations that I just introduced, the statistical approach. If the collision here proceeds through a deep well, at low temperature, you can also assume this redistribution, the statistical approach. Low temperature means the complex is long-lived, and therefore it makes sense to assume this is correct. This has been benchmarked for a few systems listed there. There are more. Again, this is not an exhaustive list, but this approach has been used in quite a few cases. This is an example for collisions of HD with H+. You have the rate coefficients with the quantum mechanical method on the x-axis and with the statistical method on the y-axis. And they all fall almost perfectly on the diagonal. Dashed line is a factor of 2, so this is definitely better than a factor of 2, which is in many cases sufficient for astrophysical applications. This is another example for OH plus H. Again, comparison between statistical and quantum mechanical results. This is the rate coefficient as a function of the temperature, and you see that the agreement is quite good, up to quite high temperatures. All right, so to finish, let me just summarize by saying that I think overall we have a good methodology. More and more data is available, including COMS, complex organic molecules. I gave you a few examples, but there is still a lot to do. I also illustrated the fact that in many cases, we look first at collisions with helium, but this is not sufficient. You really need to look at collisions with H2 as well, because in some cases, it's quite different. The behavior of the rate coefficients, is quite different. We need to go to higher temperatures, in particular, as far as vibration is concerned. Need to include, if you go to higher temperature, you need to include more rotational states because you can populate those levels. And again, that's, I told you about the problem with the size, the number of equations. You need to consider also ortho H2 in these cases. And then depending on the molecule and the observations, you might want to look at deuterated molecules, the fine structure, hyperfine structure, conformational isomers, which behave again differently. Two isomers do not behave in the same way through collisions. So overall, my conclusion is that we need new approximate methods because it's not possible to do all of this with quantum mechanical methods. And these methods need to be benchmarked appropriately to make sure of what we are doing and the quality of the data that we can then give to astronomers to put in their models. To finish, I'll just thank everyone involved in these works at KU Leuven, and then my collaborators, some of them who are in this room, and thank you for your attention.